I believe that one thing to really understand for gradient descent to actually make sense are regression models. These are one of the simplest models in machine learning, normally used for predicting continuous numerical values. These can vary from things like stock prices to temperatures and so on. But the real question is, how do they do this? Well, let's assume we are given a dataset for the experience and salaries of employees from a certain company, and our task is to predict the salaries that will be paid to a set of new employees with various years of experience. First thing we'll have to put in mind is that this is a regression problem because it involves predicting unknown continuous values, which are salaries in this case. The first thing we'll have to do is to understand the relationship which exists between the years of experience and the salaries in our training dataset. And this is one of the things done in the explanatory data analysis phase. So I believe the most intuitive way to do this is through plotting the years of experience against the salaries. Notice that as the years of experience increase, the salaries also increase. So in statistical terms, we say that the years of experience and the salaries have a positive relationship. One thing to note about this plot is that each data point represents an example or a row in our training data. Now, here is the most important thing to understand. Training our model on this data is as simple as fitting a straight line through these data points. Well, you might be wondering how you are supposed to fit this line through the data points. Should I just drop it here? Should I just place it here like this or like that? Or hold on, I think I should just place it here. Well, not quite. We leave this part for the computer to figure out. This is what training a regression model is composed of. It's just the computer trying to figure out where to place the line. To understand how this is done, we'll have to take a closer look at the regression model itself. As you may have already noticed, our regression model is just a straight line, and it has a mathematical equation of the form y is equals to wx plus b, where y is the predicted value, w is the model weight, x is the input value, and b is the bias term. In machine learning and deep learning, w and b are called model parameters. And it's these parameters that the model has to learn because we know all else about our model apart from these parameters, w and b. So now let's try to understand how these two parameters affect the orientation of the line. So we will give them random values. You will realize that the weight changes the orientation of the line, and the bias term shifts it up and down. So now, how do we know the best position and orientation of the line to be in? Or what's the best combination of the parameters? Well, this is where error functions or loss functions come in. The major thing with model training is to find the best combination of the parameters w and b, which are the weights and biases that minimize the loss function. But what is a loss function anyway? Well, first we need to understand how errors are measured in regression and in machine learning in general. An error is simply the difference between the model's predicted value and the actual value. For example, suppose a model is fitted to the training data with the following parameters. The key thing to observe is what the model predicts, whether its predictions are close to the correct y values for the given x values. To determine the error the model has made, we subtract the actual y value from the predicted value. Note that sometimes the error will be negative, but we really don't care about the sign of the error. Instead, we either take the absolute value of the error or square it. This ensures that all errors are positive. This process is repeated for all data points in the training dataset. To measure the model's overall performance, we sum up all squared errors for all data points. And the reason why the error of this point is 0 is because the model correctly predicted its y value. And we then divide by the total number of data points, giving us the mean error. This is what we call the mean squared error loss function. Another method is to sum the absolute errors of all data points, dividing by the total number of data points, giving us another loss function called the mean absolute error. These are the commonly used loss functions for regression tasks. So finally, putting it all together, model training means searching for a combination of model parameters that minimize a loss function. And this cuts across from machine learning algorithms to deep learning. Since we saw earlier that the MSE loss has the following equation, and that our regression model is of the form, we can simply unify them together into one single function with two learnable parameters, W and B. So this unified equation of the loss function lays the foundation onto which gradient descent is built. Let's ignore the bias parameter for now and only work with the weight parameter. Upon plotting, the MSE is a continuous bowl-shaped curve, which also means that we can easily investigate its gradient at different points of W. To learn the best possible parameters that minimize the loss function, the model uses an algorithm called gradient descent. This algorithm iteratively adjusts the parameters of a model based on the gradient of the loss function at the current parameter values. Where W new is the new weight value, W old is the old weight value. Alpha is called the learning rate, which controls how fast the model learns. And this is the gradient of the loss function at the current parameter value. So, first things first, in machine learning, before training a model, it's always a good idea to first standardize the dataset. This ensures that all features are on the same scale and with a mean of 0 and a standard deviation of 1. This helps the model learn more efficiently. So from now onwards, we shall be working with a scaled version of the dataset. Since we are working with a model with only one parameter, for each parameter value between any range, for example, -3 and 3, we will calculate its corresponding MSE loss for all examples in our dataset, creating a plot of W against loss J. This will help us examine how the loss reduces for each parameter during gradient descent. Let's set up our training environment. First, we've already chosen the model and the loss function to use. Gradient descent requires the gradient of the loss function with respect to W, which is simply the derivative of the loss function with respect to the weight. We have our training data and our plot. We then initialize our model with a random parameter value and set the learning rate to 0.06. Oh, by the way, learning rates are usually small values. Having everything we need, let's start training the model. So now, let's try to break down each step. First, we will calculate this sum throughout all examples in our dataset. and then substituting for n, which is the total number of examples, followed by substituting the old parameter or the current parameter, which is in this case 3.6, giving us a new parameter value of 3.28. So, as you can see on the plot, the new parameter reduced the loss function by moving a single step down towards the global minima. So, this whole process is called an epoch. And the same process happens all over again until a minimum loss is reached. As you can see, the step sizes keep on reducing as the model approaches the global minimum. Let's try to see how this process affects the fitted regression line. Also, let's try and experiment and see what happens when we make the learning rate huge, 0.9. As you can see, this makes the model bounce around, making the learning process unstable. It's now time to bring back the parameter we dropped. Everything essentially remains the same. The only difference is that there will be two gradient steps, each for a single parameter. We find the gradient with respect to the weight. followed by the gradient of the loss with respect to the bias. The more parameters the model has, the more gradient descent steps. Everything remains the same apart from the extra gradient descent step which the model calculates for the bias parameter, and this is done concurrently. This is how the loss plot for this model looks like. It's in 3 dimensions because of the extra bias parameter. Now let's experiment with different datasets. Gradient descent enables the model to learn all kinds of relationships which exist between features in all datasets. The concept of gradient descent lays foundations onto which more sophisticated optimization algorithms are built. Things like ADAM, adaptive momentum, mini-batch, stochastic gradient descent, and so on. Let me know if you found this video helpful, and thanks for watching.